So, is the screen visible to everybody and am I audible? Can anybody just unmute and let me know if I am audible?
Hello.
Yes, I'm audible, right?
Yes.
I'm
Yeah, good evening, sir.
yeah.
Yes, you are audible. Clean is visible. Clear.
Okay, okay. Thank you. Then let us continue. Let us start. Okay. So, good evening, everyone. Uh, I welcome all of you to the 12th live session of the course Concepts of Thermodynamics, which is being taken by Professors Dr. Suman Chakravarti and Dr. Aditya Bandapandhay from IIT Kharagpur. As in for myself, I am Abhik Deb and a PMRF Research Fellow in the Department of Mechanical Engineering at IIT Bangalore, and I shall be dealing with the live sessions of this course, wherein we will be solving some of the problems related to the concepts that were discussed in the previous class of the session, and so as to help you with the problem solving related to those concepts. So yeah, so today we will be solving problems related to uh, Rankine cycle and refrigeration cycle. So yeah, let us dive into it. So yeah, so for a given set of the operating pressure limits of a Rankine cycle, superheating the steam beyond the saturation temperature at the boiler pressure will result in which of the following changes in the cycle. So this the first problem relates to the Rankine cycle, and in an ideal Rankine cycle, this is the TS diagram of an ideal Rankine cycle. 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So 1 to 2 is an isentropic expansion process in the boiler. 2 to 3 is the heat rejection in condenser. 3 to 4 is the isentropic compression in the pump, and 4 to 1 is the heat addition in the boiler. So just let me write down. So steps in the Rankine cycle. 1 to 2, this is a isentropic expansion in turbine from the boiler to condenser pressure. 2 to 3 is the constant pressure heat rejection in the condenser. 3 to 4 is again an isentropic compression in pump from condenser to boiler pressure. and 4 to 1, this is the constant pressure. Heat addition in boiler. Okay. This is the process in which there is a modification basically. So it has stated that we in a general ideal Rankine cycle, if we superheat the steam, uh, superheat the steam beyond the saturation temperature. So this is the saturation temperature. Okay, so beyond the saturation temperature, if we are superheating the steam, then what will be the changes in the cycle? So this is the degree of superheat 1 to 1 dash. So 1 to 1 dash, this is superheating of steam. Okay, so due to this superheating, what is happening? See, due to this superheating, initially it was at 0.2, but now this is increasing to it is moving to 0.2 dash. So what cases are given? An increase in the thermal efficiency of the Rankine cycle. Okay, so let us see that if due to this superheating, the efficiency of the Rankine cycle is increasing or decreasing. Okay, so due to superheating, okay, the turbine work, see, due to superheating, what will happen? The turbine work, this is the turbine work. So initially the turbine work was 1 to 2, so now it is 1 dash to 2 dash, so the turbine work has increased. Okay, but the pump work remains the same. Okay, WT increases and pump work remains the same. So W net increases. Okay, W net increases, but you can also see that when the point moves to 1 dash, the heat addition also increases. Okay, but heat added, this Qn also increases. Okay, therefore from this, since W net and efficiency is what? Efficiency is W net by Qn. So from this we cannot ascertain, since both are increasing, we cannot say that the efficiency is increasing or not. Now let us consider the concept of the mean temperature of heat addition and rejection. Okay, so you can see that initially the process was up to the heat addition process was 4 to 1, so the mean temperature of heat addition was somewhat like in between 4 to 1. Okay, now the heat addition process becomes 4 to 1 dash, so the mean temperature of heat addition will be something between 4 to 1 dash, and which will be higher than 4 to 1. Okay, so the mean temperature of heat addition increases due to superheating. The mean temperature of heat addition increases. And the mean temperature of heat rejection see the mean temperature of heat rejection, there is no change. Okay, so the mean temperature of heat rejection remains same. Okay, we know that if the mean temperature of heat addition increases or the mean temperature of heat rejection decreases, then the efficiency increases. Here the mean temperature of heat rejection is not changing, but the mean temperature of heat addition is increasing, so the efficiency of the cycle will increase. Therefore the thermal efficiency of the cycle increases. Okay, this is thermal efficiency of the cycle increases. That is option number A is correct. Okay, now an increase in the moisture content of the steam leaving the turbine. Now initially the point was the turbine exit point was 2, now it is 2 dash, so the quality is improving from 2 to 2 dash, so the moisture content is decreasing, it is not increasing. Okay, so due to superheating the quality of steam at turbine exit increases from 2 to 2 dash, so the moisture content decreases. Okay, so the option B is not correct. A decrease in the amount of heat rejected in the condenser. See, initially the amount of heat rejected in the condenser was 2 to 3, now it is 2 dash to 3 dash. So 2 dash to 3 dash is will be high, more than 2 to 3. That is a change in the enthalpy. If we take, then H2 dash minus H3 will be higher than H2 minus H3. So the amount of heat rejected in the condenser will be more. Due to superheating, the amount of heat rejected in the condenser increases from 2 to 3 to 2 dash to 3. Okay, so it says that there is a decrease in the amount of heat rejected, so option C is also incorrect. Now the last option is an increase in the mean temperature of heat addition. Okay, so we have already seen that due to superheating the mean temperature of heat addition increases. So due to superheating the mean temperature of heat addition increases. So this is option number D. So the correct options are A and D. So correct options are A and D. Okay. Okay. So is there any doubt If there is any doubt, please do ask.
Sir, hello, sir. Hello.
Yeah, hi.
Sir, can you explain the mean temperature of heat addition?
Yeah, see, mm, the mean temperature, see, so there is the heat is being added from the point 4 to 1. Okay, so a portion of the heat will be added at the temperature equal to T1, and some of the portion of the heat will be added between the temperature T4 and between T1, like this. Okay, so when we take an average, like uh, suppose let us say this is 100 and this is 150 degrees Celsius, then some of the heat will be added at 100 degrees, then some of the heat will be added at 110, then some of the heat will be added at 120, and some of the, and going on, some of the heat will be added at 150 degrees Celsius. So when we take an average, like what amount of heat, I mean, at what average temperature, suppose a 1000 kilojoule of heat is being added in total. So now this 1000 kilojoule, suppose 100 joule is added at 100 degrees Celsius, then another 100 joule is added at 110 degrees Celsius, like that going on. So the entire average if we take, then there it will, at what temperature the entire heat is being added, that is a average temperature of that will lie between 100 and 150 degrees Celsius, that is T4 and T1. So that is the mean temperature of heat addition in which it is being added. So is it clear to you?
Yes, sir. Means if it is the superheating,
Hmm.
then heat addition is from 4 to the 1 dash.
Yeah.
So average temperature of the heat addition will be the increase.
Yeah, so suppose now initially we were
Because
taking
heat addi-
the heat average, the temperature average from 100 to 150. Now suppose we are separating it to
up to the
200.
1 dash.
So
Up to
we
the
will
1
take
dash.
an average from 100 to 200. So it
Yeah,
will
yeah.
increase.
Okay, okay, sir. Clear, sir. Thank you.
Okay, okay. Okay. So again in the Rankine cycle with superheat, here now we were considering a Rankine cycle which by default has a superheat. Okay, with water as the working fluid. Now if the boiler pressure is increased, this is the boiler pressure, right? 4 to 1 is a constant boiler pressure process. Pressure heat addition in the boiler. So if the boiler pressure is now increased without changing the maximum value of the temperature, now the maximum value of the temperature happens at the final degree of final position of superheat. Now without increasing or without changing this maximum temperature, if we are increasing the boiler uh, pressure, okay, and the condenser pressure is also not changing, then what will be the changes in the cycle? Okay, okay, so yeah, so keeping the maximum temperature and condenser pressure constant, if boiler pressure is increased, then mean temperature, see, though the initially the temperature was the mean temperature of heat addition was from 4 to 1. Now the mean temperature of heat addition is from 4 dash to 1 dash. So both of these temperatures, I mean 1 dash and 1 are same, but the this starting point of heat addition, starting temperature is increasing. So the mean temperature of heat addition will increase. the mean temperature of heat addition increases, and mean temperature of heat rejection remains same. Okay, therefore the thermal efficiency of the cycle increases. So the option number A is correct. Now the moisture content of the steam leaving the turbine will increase. Now see, initially it was the exit point of the turbine was 2. Now it is 2 dash. The 2 dash has a lesser quality than 2, so the moisture content will increase. Okay, so the turbine exit point at the turbine exit point the quality of steam decreases from 2 to 2 dash. So the moisture content of steam increases. Okay, the moisture content is increasing, that is the point B is correct. Okay, now the heat rejected in the condenser will increase. See, the heat rejected was initially H2 minus H3. Now the heat rejected is H2 dash minus H3, but which is lesser, so the heat rejected in the condenser decreases. So this option, the heat rejected in a condenser will increase, it is given, but this is not correct. Now the mean temperature of heat rejection in a condenser will decrease. As we have already seen that the mean temperature of heat rejection remains the same. So the mean temperature of heat rejection in the condenser does not decrease. Okay, so the option D is not correct. So the correct options are A and B. Correct options are A and B. Okay, so is it clear to everybody? If it is clear, or if there is any doubt, then you can ask. Okay, there is no doubt.
Yes, sir, it is clear, sir.
Okay,
No.
okay, then we will move on to the next problem. Now this is a numerical problem. So okay, so a steam power plant operating on an ideal Rankine cycle, it is stating, has a high pressure of 5 megapascal and a low pressure of 15 kilopascal. The turbine exhaust state should have a quality of at least 95%, and the turbine power generated should be 7.5 megawatt. The boiler, what under these operating condition, what is the boiler exit temperature for the plant? This is the boiler exit temperature. So the boiler is from 4 to 1, and the boiler exit is at 1. So we have to determine what is the temperature at this point. What we are given, that the pressure at the points 1 and 4, that is the high pressure, is 5 megapascal, and the pressure at points 2 and 3 is 15 kilopascal, that is the lower pressure. And also the turbine exit should have a quality of at least 95%, that is the quality at the state point 2 should be 95%, and the entire the power generated should be 7.5 megawatt. Okay, so the turbine power generated, not the entire power, that is the net, not the net work done, but the turbine power, that whatever the power that the turbine is generating is 7.5 megawatt. So what we are given is P1 is P1 equals to P4 equals to 5 megapascal, P2 is equal to P3 is equal to 15 kilopascal. Okay, and X2 is equal to 95%. Okay, now corresponding to this, corresponding to P saturation equals to 15 kPa. Okay, so corresponding to this saturation condition in a condenser, okay, SF equals to 0.7543 kilojoule per kg Kelvin. These are from the steam tables. SF and SG is equal to 8.0091 kilojoule per kg Kelvin, and HF is equal to 225.85 kilojoule per kg, and Hg is equal to 2599.36 kilojoule per kg. Okay, so what is S2? S2 is equal to 1 minus X2 into SF plus X2 into SG. Okay, so 1 minus 0.95 multiplied by 0.7543 plus 0.95 into 8.0091. Okay, so this value comes out to be 7.6463 kilojoule per kg Kelvin. Okay, and H2 will be same, 1 minus 0.95 into 225.85 plus 0.95 into 2599.36, and this value is 2480.68 kilojoule per kg. Okay, so okay, so S2 and H2 we have found out. Now, if we consider the turbine to be a reversible and adiabatic, that is, if we consider 1 to 2 to be an isentropic process, that is reversible and adiabatic process, okay, so the entropies will remain the same, that is 2 to 1 will be same. So, considering the turbine to be reversible and adiabatic, considering the turbine to be reversible and adiabatic, okay, S1 is equal to S2. S1 equals to S2 is equal to 7.6463. 7.6463 kilojoule per kg Kelvin. Okay. Now from the superheated table for water, corresponding to 5 megapascal. When entropy is 7.6218 kilojoule per kg Kelvin, then the temperature is 750 degrees Celsius and the entropy is 4010.56 kilojoule per kg. And when the entropy is 7.7347 kilojoule per kg Kelvin, then the temperature is 800 degrees Celsius and the enthalpy is 4128.85 kilojoule per kg. Okay, therefore for S1 equals to 7.6463 kilojoule per kg Kelvin, the temperature is what? T1 is equal to 750. We are doing the interpolation now. 800 minus 750, and this is 7.7347 minus 7.6218, and this is 7.6463 minus 7.6218. So this value comes out to be 760.85 degrees Celsius. Okay, and H1 is equal to 4010.56 plus 4128.85 minus 4 minus 4010.56 divided by 7.7347 minus 7.6218 and 7.6463 minus 7.6218. So this value comes out to be 4036.23 kilojoule per kg. Okay, so therefore the required boiler exit temperature is equal to T1 is equal to 760.85 degrees Celsius. Okay, so this is the boiler exit temperature. Now in the next part of the problem is, in the previous problem we have to determine what is the mass flow rate of the steam for the desired power output. Now what is the power output? Turbine power output is net is 7.5 megawatt. Now that power is equal to what? H1 minus H2 multiplied by the mass flow rate. So here H1 is equal to 4036.23 kilojoule per kg and H2 is equal to 2480.68 kilojoule per kg. Therefore work done by the turbine Wt is equal to this mass flow rate of the steam H1 multiplied by H1 minus H2. So the mass flow rate of the steam is what? This specific work done by the turbine divided by the total work done by the turbine. This is the total work. So it will be capital this one. Okay, divided by H1 minus H2. So this is, it is given as 7.5 megawatts. So 7.5 into 10 to the power 6, and this is 4036.23 minus 2480.68. This is in kilojoules, so 10 to the power 3. So this value comes out to be 4.82 kg per second. Therefore, the required mass flow rate of the steam (4.82 kg per second). Okay, so this is answer. So is it clear to everybody? It is clear, then we will move on.
Yes, sir.
Okay. Okay, then we will move on to the refrigeration problem now. Okay. So this is a problem of a refrigerator. Now the refrigerator will be operating on, you, you can say, the reverse of this cycle, reverse of this Rankine cycle. Okay. So a refrigerator has a steady flow of R22. R22 is a refrigerant as saturated vapor at minus 20 degrees Celsius, um, and minus 20 degrees Celsius into the adiabatic compressor. Okay, so yeah, so this is the cycle of the refrigeration. This is you can say the point from 1 to 2. This is the compressor. The 2 to 3 is the heat rejection in the condenser. 3 to 4 is the throttling or the expansion process, and 4 to 1 is the heat absorption in the evaporator. Okay, so it is stated that R22 as saturated vapor at minus 20 degrees Celsius into the adiabatic compressor. Now adiabatic compressor we are first taking 1 to 2. This is a reversible and adiabatic process. So the entry point of this is a saturated vapor at minus 20 degrees Celsius. Okay. So from what else is given from in the compressor, so this point, this entry point pressure, it is given as given, we write it down only, given P1 is equal to P4 is equal to, sorry, not P1 and P4, is T1 and T4. T1 is equal to T4 is equal to minus 20 degrees Celsius. Okay, at and T1 is saturated vapor. The compressor 1 to 2 is initially, because it is stated as a adiabatic compressor. Now from the compressor compresses it to 1000 kPa, that is the pressure, that is P2 is equal to P2s, sorry, P2s is equal to P3 is 1000 kPa. Okay, and after the compressor the temperature is measured to be 60 degrees Celsius. Is the temperature at 2s, T2s is 60 degrees Celsius. Okay, okay, and these are some of the other property data given, that is corresponding to these pressures and temperatures. What are the enthalpy values and entropy values, and in the superheated region we have to find what is the specific work input to the actual compressor. Actual compressor now. So the actual compressor is not the actual compressor is not up to 2s. The actual compressor is up to 2. So the temperature is measured in the actual compressor itself. So the temperature at the exit of the compressor, that is obviously if you are measuring the temperature, then it will be an actual compressor only, right? So the actual at the exit of the actual compressor, the temperature is 60 degrees Celsius, that is T2 is 60 degrees Celsius, and we have to find what is the specific work input to the actual compressor. Okay, now at state point 1, corresponding to T saturation is equal to minus 20 degrees Celsius equals to minus 20 degrees Celsius. Okay, H1 is equal to Hg. This is equal to 242.06. It is already given at minus 20 degrees Celsius. Okay, Hg is 242.06 and S1 is 0.9593 Hg, and S1 is equal to Sg is equal to 0.9593 kilojoule per kg Kelvin. Okay, and at the state point 2, at state point 2, this is what the state point 2 is at 1000 kPa and 60 degrees Celsius. Okay, so 1000 kPa and 60 degrees Celsius, enthalpy is 286.97. So H2 is 286.97 kilojoule per kg, and the entropy is 0.9893. So 0.9893 kilojoule per kg. So what is the required specific work input? Required specific work input to compressor to actual compressor actually. So this is the actual compressor. This is equal to H2 minus H1. Okay, so this is 286.97 minus 242.06, 242.06. So this value is 44.91 kilojoule per kg. Okay, so this is the answer. Now in the previous problem, what is the specific heat transfer to the hot place? The hot place is the condenser. Okay, so what is the specific heat transfer to the hot place? What is the specific heat rejection in the condenser? Now corresponding to saturation pressure of 909.9 kPa, okay, HF is 68.67 kilojoule per kg. Okay, these values are all given here. Corresponding to this saturation pressure, these are the enthalpy and entropy values. So I'm just writing those down, HF and HF is this one and SF is 0.2590 kilojoule per kg Kelvin, and corresponding to P saturation of 1043.9 kPa, the enthalpy of the liquid phase is 74.91 kilojoule per kg and SF is 0.2797 kilojoule per kg Kelvin. Okay, so we are trying to find out the enthalpy value at the set point 3, okay, which is the saturated liquid phase corresponding to this pressure. Okay, so at the state point 3, where P saturation is actually 1000 kPa, so we can find it out by interpolation. So H3 is equal to HF is equal to 68.67 plus 74.91 HF at P saturation equals to 1000 kPa, okay, minus 68.67 by 1043.9 minus 909.9, okay, and so this is just interpolation. So this value comes out to be 72.86 kilojoule per kg. Okay, therefore the specific heat transfer to hot space this is equal to the specific heat loss in the condenser this is equal to H2 minus H3, that is 286.97 minus 72.86, so this is 214.11 kilojoule per kg. Okay, so this is the heat loss in the condenser. So is it clear till now?
Yes. Okay, sir.
Okay, then okay, so the next part of the problem. So in the previous problem, we have to determine what is the specific heat transfer to the cold place. Okay, so you see now this is 3 to 4 is a throttling device, that is a expansion in a this is an expansion process. It is, you will see that this will be an isenthalpic expansion. How? Let us see. So considering the throttling device as a control volume, now dE by dt, this is equal to, here writing the energy equation, okay. So for a steady state process, here d by dt is equal to 0, steady state. Okay, there is no heat added, there is no work done. Okay, and mi is equal to me. Change in kinetic energy is 0 and change in potential energy is also 0. So this is 0, this is 0, this is 0, mi and me are equal, so this gets cancelled and the changes in the kinetic and potential energy is neglected. Therefore we will find that hi is equal to he. Here that is h3 is equal to h4 for the throttling device. Okay, hi is h3 and he is h4, so h3 is equal to h4. Therefore h4 is equal to 72.86 kilojoule per kg. Okay, therefore the specific heat transferred from the cold space, that is what heat is the refrigeration system taking from the space which is being actually cooled down. That is, suppose when the refrigeration system of a refrigerator, it is cooling the inside of the refrigerator, so this is a cold space. So the that is specific heat gained in the evaporator. Okay, so this is basically h1 minus h4. So all these values are known, 242.06 minus 72.86. So this value is 169.20 kilojoule per kg. Okay, so this is the specific heat transferred from the cold space. Okay. Now in the previous problem we have to determine what is the coefficient of performance of the actual cycle. What is the coefficient of performance? Coefficient of performance is, for a refrigeration system, it is basically the heat that is being taken away from the evaporator or the cool space divided by what is the work input in the compressor. Okay, so the coefficient of performance of actual cycle, this is equal to heat gained from the evaporator and work input to the compressor Okay, so this is basically H1 minus H4 is the heat gain from the compressor, and this is H2 minus H1. Okay, since this is the actual compressor, we are taking H2. Okay, so this is 169.20 and this is 44.91. So this value is 3.77. So the coefficient of performance of this is 3.77. Okay. So again, in the previous problem, determine what is the isentropic efficiency of the compressor. See, we have considered that this actual compressor, right, up to 2, but there in the isentropic compressor will be compressing this refrigerant vapor to the point 2s. Okay, wherein the entropy will remain same, that is s2s will be equal to s1. Okay, so we have to determine what is the isentropic efficiency of the compressor. Okay, so for isentropic compression, Okay, the entropy will remain the same. H2S is equal to S1 is equal to, what is S1? S1 is 0.9593 kilojoule per kg Kelvin. 0.9593 kilojoule per kg Kelvin. Okay, now corresponding to these all 2s, all of these are in the pressure of the condenser, that is 1000 kilopascal. So corresponding to 1000 kPa, see, corresponding to this entropy we have to find the enthalpy, right? So in this we are in the given data, see, in corresponding to 1000 kPa and corresponding to these entropies, the different enthalpy values are given. So from this we will be doing the interpolation. So when entropy is 0.9400 kilojoule per kg Kelvin, okay, the enthalpy is 271.04 kilojoule per kg, and when entropy is 0.9651 kilojoule per kg Kelvin, the enthalpy is 279.05 kilojoule per kg. Okay, therefore corresponding to the point 2s, okay, where H2S is equal to 0.9593 kilojoule per kg Kelvin, H2S is equal to, we are doing the interpolation now, 271.004 plus 279.05 minus 271.04 by 0.9651 minus 0.9400, and this is 0.9593 minus 0.9400. So this value comes out to be 277.20 kilojoule per kg. Okay, so isentropic compression work will be what? Isentropic compression work is this one. This is the actual compression work, and this is the isentropic compression work. From 2s to 1 to 2s is the isentropic compression work, and 1 to 2 is the actual compression work. For isentropic compression work, W isentropic, this is equal to H2S minus H1. Okay, so this is 277.20 minus 242.06. So this is 35.14 kilojoule per kg. Therefore, isentropic efficiency of the compressor is equal to what? This is the isentropic compression work by actual compression work. The isentropic compression work is H2S minus H1, and the actual compression work is H2 minus H1. Okay, so you see that H2S minus H1, that value will be lesser than this value. Okay, that is in H2S minus H1, that is the isentropic compression process. That is basically an ideal compression process in which the minimum amount of work will be required. But when it is not uh, isentropic, that it is not reversible adiabatic, when it is an actual compressor, then there will be losses. So the compression work will increase. So the compression work will be H2 minus H1. Okay, so these values we have already determined. So this is 35.14 and the actual compression work is 44.91. So this value is 0.7824, or this is 78.24%. So this is the isentropic efficiency of the compressor. Okay. Okay. So is it clear to everybody?
Hello, sir.
Yes. Hello.
Yes, yes, it is clear.
Okay.
Sir, these things are just opposite in the turbine, I think.
Sorry.
In the turbines,
Hmm.
that actual work is the less and the isentropic work is the more.
Yeah. In the
Yeah,
turbine, this is a compressor. So if we consider, see here,
yeah,
if we
yeah,
consider this, so
yeah,
the actual work is 1 to 2, but in isentropic work will be like this, so it will
yes,
be lesser. Okay,
yes.
so in
So in
act
the turbine, if it will be the isentropic
yeah,
actual work divided by the
actual work
isentropic.
divided by the isentropic work.
Yeah, 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 sir. Okay, sir.
Okay,
Clear now.
yeah, so are all these clear to all of, I mean everything is clear, right? Okay, so uh, Uh, this is most probably the last class, mm, uh, the 12th lecture. I think so that uh, your exams are also coming. So all the best for your exams. I hope that this live sessions have been helpful to all of you for clearing some of your doubts. So mm, anyway, so I hope I have been able to add something to your concepts, and thank you for attending. So all the best for your exams. Okay, thank you. So if there is,
Sir, definitely, sir. You have added most of the thing to our knowledge. We
okay,
gain much more from this course. I really enjoyed this course. Even
okay,
Dr. Chakravarti sir, he
hmm.
is an exceptional for this
Yeah,
subject.
he is
The
actually
subject
exceptional.
of
Yes,
thermodynamics. And I know this subject is very conceptual subjects, and
yes, yes.
sir has any clear all basic that is any things very suppose simply, sir.
Yeah,
And
that is true.
sir, by you and Akshay sir also in your any live session, in the practice session, you have taken the more additional any problems different than the regular lectures, sir. And sir,
Hmm.
your any most thing I like, the thing I like is your the problem systematic way of solving the problem. Yeah, I
Thank
like
you.
that is too
Thank
much,
you
sir.
very much. Okay, so
Also, you have
uh,
clear the most of the any basic things also. Really, sir, I enjoyed the course and I get a lot more from this course. I'm lucky to learn something from Chakravarti sir and you as well as Akshay
thank you
Chate.
very much. That is actually an honor. And yeah, Chakravarti sir is really great. And
Yeah.
okay, so all the best for your exams.
Okay. Thank you.
Okay. Okay, then
Thank you,
you
sir.
may leave then. Thank you.
Okay, sir. Okay, thank you very much, sir.
Thank you.
Okay.